Yes, I'm Suman Banerjee. I'm in the group of faculty who work in broadly computer networking, although this topic and this domain has become so broad now that you can think of multiple sub-areas even under this area. So at a high level, there is three main faculty who work in broadly computer networking. It includes Professor Aditya Akela, Professor Paul Barford, and myself. And we, each of us kind of do slightly different things, and we have in fact diverged over the years. So for example, Aditya is doing a lot more systems that are more like big data systems and applications in data centers and networking in that space. Paul Barford does a lot of internet measurement-based research. Some of it applies to security, some of it applies to generally understanding how the internet is evolving over time. And I do more mobile and wireless systems, although my work has become more application-driven over the last few years. So one thing I want to mention before I tell you a little bit about our research is that we will also have an open house where some of our students will be happy to meet you guys. So that will happen in room 2310, okay, and this will be from 4 to 5. Of course, you probably have already signed up for one-on-one meetings with some of us, so you're welcome to come to the one-on-one meetings if there is any additional slots and you haven't signed up already, but if you want to meet the students, they'll be available 4 to 5 at this time in CS 2310. Okay? So, I'll tell you a little bit about networking research, what it is about, and I think it's important to realize that even though networking as a field has probably been existing for almost now 50 years or a little bit more, you know, we still have lots of interesting open problems, and these are critical problems to almost all of mankind. All of our lives depend on it, and if it were not to work, if something didn't work right, I think it will impact us in big ways. So I think there's huge opportunities, big problems, and really, I think networking, luckily, is sort of a field. I think it's true, and we're getting to for most fields these days. It actually touches upon a lot of other disciplines also. Okay, so clearly, we have a lot of techniques and mechanisms that we use from AI to machine learning to security and privacy, algorithm design, you name it. So there is lots of interesting opportunities if you're interested in being a little broader. You know, there is opportunity to do that in this field, and so that's what excites me. In fact, you know, if you look at current research that all three of us are doing, we have probably gone far beyond just doing core networking research. Okay, so let me tell you a little bit about what's involved. You know, so we all know that the big problems in networking are first to understand how the internet works. Internet is one of these unusual sort of systems that is completely man-made, and it's huge at scale. You know, we study, I think scientists study lots of large systems, but they're all natural systems. They evolve naturally when people study them. Like planets and solar systems and galaxies and lots of animals and so on, right? But internet is one unique infrastructure that is completely man-made, and it is so big. It is really hard to understand what's happening in this, even though we have scientists, researchers, and engineers who put it together. So there is a whole effort in understanding what's going on in the internet, why does it fail when it fails, and where are the failures, and how can we keep it working and scale at the same time. And the big challenge, of course, is that as time evolves, we are adding devices to it incredibly fast. I think people say that every individual now has 4 or 5 devices, and if you think of homes, your home probably has 20 devices that are all connected to the internet. The old joke in 20 years back used to be that your toaster oven will be connected to the internet. It's no longer a joke. I mean, people have all kinds of gadgets that are connected to the internet, and you have to deal with that scale. So that's actually a huge challenge. And then there is this whole wireless thing. So I think all of you are carrying at least 1, maybe 2 mobile devices in your pocket. And if you think that is hard enough, to get the capacity you need to provide all the data bits that you want to consume, whether you're watching cat videos or you're doing some actual work, it's incredible that we will do all of that over wireless. But that's actually going to be only one part of the story. there is going to be this big thing, not going to be, it's already here, what's called Internet of Things, which is, there's going to be hundreds of devices per person that are small devices sending maybe little bits of data, but they need to be separately addressable, connected, secured, and all that, right? So there's huge challenges coming down the pipe, and we probably don't have the capacity today to get all these devices in the network. Okay? And then there is this other very interesting space, which is about data centers and cloud infrastructures, which we are all using all the time, right? All the Amazons and the Googles and the Facebooks and so on. And the amount of traffic that travels within these data centers are almost as big as the amount of traffic that travels outside it, because everything goes there firstly. And so you have to deal with architecting incredibly high-speed systems that work at very low, low latencies and can give you the throughputs and the performance that you really desire. Okay? So as I said, our work probably touches almost all aspects of computing. We talk to almost all of our colleagues, and we work with them. I think we have projects with all of them collaboratively, so I think this is kind of an exciting time to be in networking as a field. Some of the animation came up later, but so some of the big opportunities I think have been happening over the last decade, and it's going on. So there's been developments like software-defined networking. How many of you have heard this term? Okay, quite a few. So this has really been transformative, right? So there used to be these big companies like Cisco's and Junipers that would sell really large routers, basically compute platforms that all they do is take packets from one port and forward it to another port based on destination IP or something like that. And these are very expensive. They cost in hundreds of thousands of dollars to maybe even approaching $1 million per unit, depending on the size and scale of it. They are proprietary, closed system, and only large companies will put it in, like ISPs, like AT&Ts, and are challenging to maintain and manage. And software-defined networking came about and basically said, why do we need proprietary hardware and proprietary systems to do this? We will actually transform all this and do it in software. And we will use off-the-shelf boxes, maybe running Linux, and of course, better quality boxes than probably your laptop. But still, they're a lot lower in cost and much easier to manage because of the structures of it. But it opened up this industry, it completely transformed this industry in big ways. And now, this is sort of a big push to make a lot of networking be software-defined. Okay. Then there are software-defined network devices. You're slowly moving towards not having dedicated hardware as firewalls and various intrusion detection systems and so on. They're all also moving in software, and they can be pushed to the cloud. They can be migrated to various locations. So lots of interesting opportunities are coming up there. I briefly touched upon the need for high speeds. So today, you can probably get, if you're lucky, you can get maybe tens to hundreds of megabits per second on a cellular network. If you're in a Wi-Fi network like you're right now, you can probably approach gigabit speeds, okay? But this is not going to be enough, okay? As you start moving to applications like virtual reality, augmented reality, and these are not just for fun and games only, although it can be. People will build systems that will primarily use these systems in maybe the next decade. We will need higher speeds, lower latencies. And we are already working on technologies that are being called millimeter wave. In fact, recently there was a talk in our department on terahertz communication. Terahertz, so millimeter wave is tens or hundreds of gigahertz. Terahertz, you can imagine, is much higher frequency. They have unique challenges. Designing these systems is going to be a big issue in the coming years. Vehicular systems. So we all hear about autonomous vehicles, Google and Uber and everybody's doing it. Most of these vehicles, by the name autonomous, they are completely sort of independent. They really try not to depend on any other infrastructure. Of course, they get fed a lot of data, but once they have the data, they don't kind of look at anything else. They just look at the data, they sense the environment and do what they need to do. But there is lots of opportunities that will come about when you make these vehicles connected. And this is going to happen. All vehicles are slowly getting connected. So if you look at most new models of vehicles today, they're all connected to the internet, exchanging all kinds of data. Now, if every vehicle in the world gets connected, again, it's a huge load of new kinds of data that needs to be supported. And how will that work? So these are some of the big challenges and issues that are coming up that we are interested in working on. So with that, I'll tell you now a little bit about individual projects that some of us are working on. Of course, by no means this is exhaustive. We work with a number of students. We tend to have decent-sized groups, and we always welcome people to come and join and work with us on these exciting problems. So, Paul Barford has been working on many ways of improving performance and resilience of various kinds of services on the internet. He likes to take a very empirical approach to research, so he likes to collect a lot of data, being a measurement person. He loves to get a lot of data, terabytes of data on traffic characteristics, matrices of traffic. And from that, he makes inferences, analyzes, and comes up with various interesting observations. So he has published, obviously, all of us have published well, I think. And Paul has released a lot of software and data sets to the community, which is actually great because, if you do some work and then you release your data sets, you release your software, then lots of others can use it. And they really feel, and we all feel this is a huge value to the community. So that's the style of research that I think all of us probably take, and Paul does it quite well. So some of his exciting projects have been like, mapping the internet. Now you may think, what does mapping the internet really mean? Is it drawing some lines on a paper and figuring out how links connect to each other? Well, he had this project called, I think, the Internet Atlas, which was trying to understand, we think of our network as some kind of nodes and edges, but are these nodes and edges really distinct? We think that the internet has distinct paths, disjoint paths, and that helps us give resilience, right? But are these paths really distinct or disjoint? Because many times what happens is that, if AT&T has put a conduit in one location, to one part of, connecting two cities, Verizon will come and say, oh, there's already a conduit there, I'll also draw my wires to that same conduit, right? But then what happens if that conduit breaks? Both the paths fail at the same time. So how do you infer what is the disjointedness of the internet and what's the level of redundancy? It's really important to the survival of the network. So he's done this project kind of trying to quantify that, but very widely cited. Lots of other similar projects on measuring traffic and understanding the risk that are posed to such kind of systems. Okay. So in fact, I think one of his recent work is kind of not really networking as such, but he's been looking at people's browsing behavior, and from that assessing how people are thinking of our political candidates as election years roll in. So I think that's also quite interesting activity that he's been involved in. So for me, so I work a lot on mobile and wireless systems. So one thing we do, of course, is we run a lot of infrastructure and test beds. We run our own 4G network. In fact, we will be soon trying to deploy our own 5G network on campus in and around Madison. We have something called TV5 space networking infrastructure. We have a Wi-Fi infrastructure that is a separate infrastructure for research, separate from your access network that we use. And many other things. We have deployed infrastructure on vehicles, on city buses in Madison, on long distance buses that go between Madison and Chicago. And we really kind of use them for a lot of our work. So I like to be very application focused. So instead of saying, how can I make the wireless throughput be 10 times more? I like to first start with what is the high level problem that we would like to solve, and then decide what exact aspects of the system we will try to optimize. So I'll give you a few examples. So one of the projects we've been working on with some healthcare personnel, both in campus and elsewhere, is on physical therapy. Okay, so physical therapy is very important, although I'm hoping none of you had to deal with it. It's not fun. But people, if they have a surgery or they have some old age, you have some health issues with your bones and other things, you are recommended to take physical therapy, and without that you will actually not recover, right? From a post-surgical recovery, physical therapy is important. What is physical therapy? You do some exercises, you move your limbs to a certain degree as much as you can, and you keep pushing it till you get full mobility of your limbs, right? So this is done in a very antiquated way. Basically, you go to a physical therapist, they will sort of move your arm maybe like this, they'll lift it up, you will lift it up, and they'll help you. And then they will measure using literally like a compass kind of a thing and see, okay, what is your arm motion that you were able to accomplish. You have to do this multiple times in a week. It's very cumbersome, very non-scalable. So we have been working on a system based on edge computing, which is a term you will hear a lot lately, where we put a sensor or multiple sensors on the person, and using the inertial motion sensors in those sensors, we will automatically track your motion. Okay? And we will track this continuously, not while you went to the physical therapist. You just keep it ready, just like your smartwatch or something like that. You go about your daily routine, and we are tracking how your body is able to move or not move, and we can report it, we can analyze it, we can report it, and then you can have very interesting interactions. Okay? So that's one example. Another example of a sensing plus edge computing project is a drive analytics project that I've been involved in, where we are putting similar sensors in your vehicle, and from that trying to estimate how well you drive. Okay? So I think there's a statistic that says more than 80% of drivers in the world think they're above average. Okay? Which is amazing. I think we all overestimate our skills, which is okay. It's good to be positive, but it can be dangerous when you think of that as a driver. So this is a tool, and there are lots of products out there today already that gives you some sense of how well you drive. Okay? And they use, again, IMU sensors on a vehicle, and from that they say how did you brake, how did you accelerate, and from that give you a score, and we can kind of understand how good a driver you are. So for example, this picture here, I'm going the right way. Yeah, this picture here is one of my drives going from campus almost to my home, and it tells me my speeds, where I brake poorly, and things like that. Okay, so I don't want you to read that information because it's private. Anyway, so this is so we improved upon this by also using additional audio-visual cues. So we look at the driver, and we want to understand, you brake hard, but why did you brake hard? Did you brake hard because a cat suddenly came in front of you and you were alert? Or did you brake hard because you were looking at your phone and suddenly looked up to see the car in front was stopped? And they're different. So we have started doing projects where we are now adding audio-visual cues to understand how a person's driving. So this is sort of, if I play it back again, it's going to show a driver being looked at by a camera, and other cameras that are looking at what the driver is doing when they're, for example, making a turn. Did you check your right wing mirror? Did you check your blind spot? And did you put the blinkers on before you turn? So that's sort of the systems we're building, all using edge compute support here. So we do a bunch of other projects of this type. We do some work with electric cars. We have a few on campus that is purely for research use. And we are trying to understand impact of sustainability, and we can instrument these cars as much as we want, and look at how some of these systems interact with the electric grid, for example. Okay? So that's about me. I'll spend a couple of minutes to tell you about Aditya's research. He's been really working hard to push the performance of lots of core networking systems, including cloud-based systems and data centers and so on. So one of his big projects, by the way, is this project called Cloud Lab, which is actually a desperate infrastructure to do research on cloud infrastructures. So it is like a mini Amazon data center or a mini Azure data center that is hosted at UW-Madison, and Aditya actually leads that effort. He has also been working on more of formal methods in networking. He applies a lot of programming language techniques to how you specify various rule sets, how you define various scripts that run at different nodes, and how to combine them and synthesize them in efficient ways. So you collaborate a lot with the PL faculty here. And then there are very interesting individual projects that he has worked on, where if you think of a distributed set of nodes, routers and switches and so on, you describe with their various rules that are specified at each switch, but the rules may conflict. You may say here certain traffic has to go to this switch, but that switch may drop those packets because it didn't want that traffic. But if you describe them separately at different nodes, how do you understand the global properties? And these properties can change over time, and you want to keep them consistent to accomplish some high-level goals. So how can you specify the overall requirements of a network at a high level and let the rules be populated automatically in different switches and routers? Okay. Similarly, he works a lot on understanding and optimizing data center performance, as I said. So he's been looking at things like very low-speed communication there, programmable NICs, which can support various kinds of interesting resource allocation problems. And then more recently on serverless network functions, which is again a very interesting domain that is come up in the cloud in the recent years. So he, if you have a chance, I'm sure you're getting to talk to him later today. So in summary, I would say that our networking group is very strong. If you go to say csrankings.org, and you search for any of these keywords randomly, I think you'll see that we are usually in the top few across the world. I think that's a good thing for us, and we are very proud of that. The students do pretty well. They get to go to, most of them want to go to startups or do exciting industrial jobs because there's great opportunities, but we have some folks who go and become academics. And I think our students, we are lucky to have great students, but they all tend to get good fellowships from the top places. And our faculty, we do have a good standing in our community. We love to have our students also go to internships. We have great relationships with all our industry in the space. You name a company and we have worked with them. So I hope you, firstly, I hope you come here, and we are happy to have you guys be part of our department, part of our group. And I think there are many exciting opportunities in this space. So we will all be available this afternoon, and our open house with the students will be 4 to 5 p.m. in CS 2310. Thank you very much.